Today we shall do the heat exchanger analysis. By E and PU method. E means effectiveness and T means number of transfer. So we shall find out the effectiveness of parallel fluid exchanger as well as counter fluid exchanger. Before that, we shall define what is effectiveness and what is entropy. Now see, in LMPD analysis, we have seen, suppose for counter fluid exchanger, what we have seen for LMPD analysis, this is the THI, hot fluid inlet temperature, that is hot fluid outlet temperature, and this is cold fluid inlet temperature, this is cold fluid outlet temperature. So when all the temperature, that means intake and outlet temperature of both the fluids are known, then we have analyzed the heat exchanger and we have found out the heat transfer by LMTD or log mean temperature difference. That is, we have done by LMTD analysis. Now, LMTD could be found out when all the temperatures are known. But if, suppose, for a heat exchanger, only the inlet temperatures are known to us. That is, this is THI and this is TCI. We know nothing about the outlet temperature. Outlet temperature is not known to us. Only the inlet temperature is known to us. When all the temperatures are known to us, that was for LMTD analysis. In this case, we shall do it by E and PU method. When only the inlet temperatures are known. Okay? Yes. How to do this? First, we shall define effectiveness of heat exchanger. Effectiveness. Now see, effectiveness which is denoted by epsilon. Effectiveness is defined as Q actual by Q maximum. What is Q actual and what is Q maximum? Okay. Now see, if we consider for Q actual means, suppose if it is THO and it is TCO. Then what is the actual heat transfer? For hot fluid is how much? Actual heat transfer for hot fluid is m dot h Cph THI T minus TH, and for cold fluid is m dot C Cpc TCO minus TCI. Okay? But what is the maximum heat transfer rate? What is the Q maximum? Q will be maximum when temperature difference will be maximum. Okay? What is the maximum temperature difference here? This minus this. Okay? So Q max will be written as THI minus TCI multiplied by which fluid we shall take. See, for this case either cold fluid will be heated to hot fluid inlet temperature or hot fluid inlet temperature or fluid will be cooled to such that it will be equal to the cold fluid inlet temperature. Is it possible? It is possible only when the heat exchanger is of infinite length. Clear? Yes. And the heat capacity rate of the fluid should be minimum. So it will be C minimum, C min of THI minus TC. C minimum is the for M dot H CPH and M dot C CPC. This is called CH, this is called CC. Out of this, which one is minimum? That is called C. If the heat capacity ratio is minimum, then temperature difference will be maximum. We are getting the maximum temperature difference, that means we have to take the minimum heat capacity difference. So from this what we can write? From this we can write effective days epsilon is equal to M dot H CPH. M dot H CPH would be written as CH THI minus THO divided by C min THI minus TCI. Okay, that could also be written in this way for cold fluid CC TCO minus TCI divided by C min THI minus TCI. Okay, our aim is to find out the heat transfer rate of an heat exchanger. Here, that is Q actual by Q maximum. We have to find out the value of Q actual. What is Q maximum? That is C min of THI minus TCI. Both THI, both inlet temperatures are known to us, but outlet temperatures are not given to us. Since the outlet temperature is not known to us, we have to approach to this effective days analysis. Then another term is known as NTU. NTU, that is number of transfer units. NTU defines the size of the heat exchanger. It is defined as NTU is equal to UA by C minimum. UA is the overall heat transfer coefficient. A is the area, C min is the minimum heat capacity ratio. This UA is defined as heat capacity of heat exchanger divided by heat capacity of the fluid. In heat exchanger, two fluids are flowing. One is cold, another is hot. So heat capacity of heat exchanger, that is UA, by heat capacity of fluid, which is minimum out of cold fluid and hot. Clear? So NTU is defined as UA by C. Another is defined heat capacity ratio. Heat capacity ratio. Heat capacity ratio, which is C, which is defined as ratio of C minimum by C maximum.
we have two fluids. One is cold fluid and another is hot. So heat capacity of out of this fluid, one fluid will be minimum and another fluid is maximum. So ratio of C minimum by C maximum is known as heat capacity ratio. Clear? And we will prove that effectiveness epsilon is a function of NTU and effectiveness of any heat exchanger is a function of NTU and C, number of transfer unit and the heat capacity ratio. Okay, so first we shall find out the effectiveness for parallel flow heat exchanger in terms of NTU and C. So for first we shall consider for parallel flow heat exchanger. Parallel flow heat exchanger. Parallel flow heat exchanger. To draw the T versus X diagram of parallel flow heat exchanger, this is THI and this is TCI, this is TA2, this is TC. This temperature difference, this side temperature difference is suppose delta T1, this side temperature difference is suppose delta T. Okay, this one. So this side is delta T1, that side is delta T2. Okay, we are considering one strip where temperature is TH and here the temperature is TC. So these two difference we are considering as suppose delta. So in parallel flow heat exchanger, hot fluid is coming from THI to TH2, cold fluid is coming from TCI to TC2. So this side temperature difference we have considered delta T1, which is nothing but THI minus TCI. That side is nothing but delta T2 TH2 minus TC2. At any instant or anything, we have considered temperature of hot fluid TH, temperature of cold fluid TC. At that instant, their difference is suppose delta T. Okay? So what you can write? Delta T is nothing but TH minus TC. To differentiate it, what you can write? D of delta T, which is nothing but dTH minus dTc. Can you write this?
Yes.
Now see, it is a heat exchange process. Hot fluid is releasing heat, cold fluid is taking the heat. So what is happening? Heat released by the hot fluid must be equal to the heat taken by the cold fluid. So that heat we are considering suppose delta Q. So delta Q is nothing but m dot H CPH dTH, and it is releasing, that's why it is negative, minus m dot H CPH dTH. For cold fluid it is m dot C CPC dTC. Can you write this?
Yes.
Now from these two equations, what we can write, see the value of dTH is equal to minus delta Q by m dot H CPH. Similarly, dTc could be found out as
delta Q by M dot C CTC. Okay. Now putting those values of PTH and PTC into this equation. PTH and PTC into that equation. What we are getting? D delta T. D delta T, which is equal to PTH. PTH is nothing but minus delta Q by M dot H CPH minus delta Q by M dot C CPC. So we can write minus delta Q into 1 by M dot H CPH plus 1 by M dot C CPC. Can you write this?
Yes.
M dot H CPH is nothing but capital CH minus delta Q 1 by capital CH plus 1 by capital C. Okay?
Yes, sir.
Now see, we are considering that 1 by CH plus 1 by CC is equal to some constant D. CH, CC are constant?
Yes.
Speak for some purpose.
Yes.
Okay. So we can write it D delta T, which is equal to minus delta Q minus delta Q into B. Minus delta Q means UA delta T. Internal is overall internal coefficient multiplied by the area into temperature difference. That is minus U dA delta T into B.
Yes.
Can you write this?
Yes.
Now see, this could be written in this way: E of delta T by delta T, which is equal to minus U B dA. Okay. Now we are integrate it. What is the limit from delta T1 to delta T2? Area is from 0 to A. Okay?
Yes.
From delta T1 to delta T2, here area was 0,
Yes.
then it is approaching integer, area is A. So 0 to A, delta T1 to delta T2. Now, after integration, see what we are getting: log of delta T2 by delta T1, which is equal to minus U A into 1 by CH plus 1 by CC. B is value, B is value of this. Okay? See, that position has minus UA by CC into 1 plus CC by CH. Can you write this? Now we shall put the value of delta T2 and delta T1. See, delta T2 means DHI minus TCI. So log of DHI minus TCI by delta T2
THO minus TCO divided by THI minus TCI, that is equal to minus UA by CC into 1 plus CC by CH. Okay?
Yes.
Here only the inlet temperature is known to us. Outlet temperature is not known to us.
Yes.
Okay? So what we have to do? We have to transfer all the outlet temperatures into the inlet temperature. How to do it? See, this is supposed to write it as equation number 1. Now what is Q actual? We have defined for effectiveness. Q actual is equal to epsilon into Q maximum. For hot fluid, what is the Q actual? That is m dot H CPH THI minus THO, that is epsilon into Q max is C minimum into THI minus TCI. Okay. What is Q maximum? C minimum into maximum temperature difference. Maximum temperature difference is THI minus TCI. Our aim is to find out the outlet temperature. Since outlet temperature is not given to us, so from these we can write this is the capital CH into THI minus THO, that is epsilon C minimum THI minus TCI. From these we can find out the value of THO. What is THO? That is THI minus epsilon C minimum by CH into THI minus TCI. Equation number 2. Simply we have found out the value of outlet hot fluid temperature in terms of inlet temperature of both hot and cold fluids, because only inlet temperature is known to us. So for equation number 1, THO we have found out in this way. Similarly also we have to find out the value of TCO. How to find out? By applying the same formula. So what is the Q actual for the cold fluid? For cold fluid, what is happening? That is MC, CPC, PCO minus TCI, that is equal to epsilon C minimum THI minus TCI. For cold fluid, actual heat transfer rate is m dot CPC, PCO minus TCI, and epsilon C min THI minus TCI. M dot CCPC, that is nothing but capital CC. PCO minus TCI, that is epsilon C min PHI minus TCI. So from that we can find out the value of TCO. What is TCO? That is epsilon C min by CC. Epsilon C min by CC THI minus TCI plus TCI. Equation number 1. See, in equation number 3, there is also no outlet temperature. Only the inlet temperatures. Because only inlet temperatures is known to us. Now we shall put the value of THO and TCO from 2 and 3 into equation number 1. How to put it? Just simply put the values. See, in equation number 1, we shall put the value of THO and put the value of TCO. See, one more. You can write it as using the logarithm sign, or you can write from here we are getting it C THO minus TCO by THI minus TCI, that is equal to means exponential minus UA by CC into 1 plus CC by CH. Okay. Now put the value of THO and TCO from equation number 2 and 3. Just simply putting the value of THO and TCO from equation number 2 and 3. So just first putting the value of THO, that is nothing but THI minus epsilon C minimum by CH THI minus TCI, that is for THO minus epsilon C minimum by CC THI minus TCI plus TCI. Divides by THI minus TCI, which is equal to exponential minus UA by CC 1 plus CC by CH. Okay. Clear? We are simplifying it once again. See, this THI minus TCI. And what? And this THI minus TCI and THI minus TCI we are taking as common factor. Multiplied by epsilon into C min. So minus epsilon C min THI minus TCI is cancelled out. So that is 1 by CH minus 1 by CH. That is equal to exponential minus UA by CC into 1 plus CC by CH. The minus will pass over, it will pass. So this is minus, this is minus. Okay. So what we can write? minimum by CH, that is 1 plus C minimum by CC. So 1 plus CC by CH. Okay, that would be written as exponential minus UA by CC into 1 plus CC by CH. Our aim is to find out the effectiveness of parallel flow. So you want to find out the value of epsilon. So next step, if you write it, what you shall get? Next step, you shall get epsilon is equal to C is 1 minus. See, we have done something, one small mistake. 1 minus this one. Okay, so that is 1 minus exponential minus UA by CC into 1 plus CC by CH divided by C minimum by CC into 1 plus CC by CH. Okay? Yes, sir. Now see, two fluids, one is cold and another is hot. So one should be minimum and another should be maximum. If we consider CC is minimum and CH is maximum, okay, then C is equal to, by definition, C is equal to C minimum by C max, which is nothing but CC by CH. And NTU is nothing but UA by C min. That is nothing but UA by CC. So applying this, what we shall get? 1 minus exponential minus UA by C min into 1 plus C min by C max divided by C min by C min into 1 plus C min by C max. That is 1 minus exponential minus NTU into 1 plus C by 1 plus C. That is the heat exchange effectiveness for parallel fluid. Now, see, we have considered CC is minimum and CH is maximum. If we consider CH is minimum and CC is maximum, it will do it same result. Here, you can check it. Okay, so that is the effectiveness for parallel flow heat exchanger. Okay. Yes.